Alright, so before we get started on our study of forces and later on projectile motion, we first need to understand the concept of vectors. Now, vectors are just quantities that have both a magnitude or a size. They mean the same thing. They also must have a direction in which they are oriented. Now, vectors are represented by an arrow, and we use the length of that arrow to represent the size of the vector, and the direction in which it's oriented will represent the direction. How we determine that direction is if we look at a horizontal line, how far above that horizontal line clockwise do we go? This one looks to be maybe 50 degrees from the horizontal, so we'll draw it 50 degrees. If it were straight up, it would be 90 degrees. If it went all the way over to the left, it would be 180 degrees. Going down, it'd be 270 degrees from the horizontal. And finally back around to straight right would either be 0 degrees or 360 degrees, both being the same value. Well, let's just pretend we have this vector here oriented at 50 degrees. We'll say that it is 3.6 meters in length. Now, one useful thing that we want to do with vectors is to break them down into what's called their components. So let's again draw this vector of 3.6 meters at an angle of 50 degrees. Every vector can be broken down into two components. Usually an x component and a y component. So let me erase this. The x component, notice, ends up being the length of the vector. The y component ends up being the height of the vector. As if I were to walk in two different directions, I could go from the tail of that vector to the tip of it. Now we're going to want to know how to calculate the two components of this vector. We can just use simple trigonometry to do that. So first, let's calculate the red horizontal vector. We know that the cosine of an angle is defined as the adjacent side of a triangle to that angle over the hypotenuse of that right triangle. In this case, that's going to be the x component that we're trying to find. Let's call this vector r. So in this case, we're looking for the x component of r over the hypotenuse, which is r itself. We can rearrange this equation to say that the x component equals r cosine theta, or 3.6, which was my magnitude, times the cosine of the angle 50. So I go ahead and put that into my calculator. I get a value of 2.31 meters. So that means I've gone 2.31 meters to the right. I also want to know how far up I've gone. So similarly, to find the y component, I take the magnitude times the sine of the angle. So I get 3.6 sine of 50. And I'm going to end up with 2.76 meters. So I can double check that. I can put 2.31 squared plus 2.76 squared. That should be equal to r squared, or 3.6 squared. When we put that into our calculator, we find that r squared is equal to 12.95, or r equals 3.6. So it all checks out. So this is a very important aspect. Note that sometimes the x component might not be associated with the cosine. Usually it is, but the important thing is to realize that the side associated with cosine is the one that this angle touches. The opposite one is associated with sine. Alright, so let's look at another example. Let's look at if we only know the components of a vector and we want to find the resultant vector. So let's say we know this vector h. The x component is 2.71, we'll say newtons, which we'll find is a unit of force. The y component is 8.86 newtons. We want to find h, the total vector, when you add that 2.71 newtons and that 8.86 newtons. What's that final vector that those two are going to add together to give me? In order to find that out, I'll use the Pythagorean theorem. I know this is 8.86. I know this is 2.71 in the x direction. So 2.71 squared plus 8.86 squared will equal my resultant vector squared. So then, after I do the math, my magnitude of my vector should be 9.27 newtons. Now to find the angle, it gets a little trickier. But I have all three sides of this right triangle formed by the components in the resultant. So I can use any three of the functions, of the trig functions. Since these two values are right here, these are the adjacent and the opposite sides to my angle. So I'll just go ahead and use tangent. Tangent of theta is going to equal my opposite side, or 8.86, over my adjacent side, which is 2.71. This means that tangent theta is equal to 3.27. If I take the inverse tangent of each side, I get theta is equal to inverse tangent of 3.27. And on my calculator, I'm going to find that to be 72.99 degrees, or 73.0 degrees. Make sure in your calculator you have that set to degrees. Radians won't give you the correct answer for a lot of these problems we're going to do, unless it specifically specifies radians. Now, finally, we want to know how to add various vectors. There's a couple methods we can use for that. The method we're going to look at is if we have two vectors. They can be placed anywhere in space. The first thing we want to do is bring them together. So we're going to put this, we'll move this blue vector. Actually, let's move the green vector to be over toward the blue vector. So as you can see, it doesn't matter where this vector is located, as long as I draw it with the same length and the same angle, I can add these two vectors together to get a resultant vector from the tail of the first to the tip of the second. Sorry, my lines are a little curvy there. Let me try to draw a better demonstration for you. In other words, if I have one vector here and one vector here, the sum of those two vectors is going to be from the tail of the first to the tip of the second. One way to do this is we can break the first one down into its x and y components, and then we can break the second one down into its x and y components, and we can add all the x and y components to find the x and y components of the sum. So let's go ahead and look at an example here. Let's say we have the vectors we'll say we have vector A is 3.26 meters per second at an angle of 20 degrees. And we have vector B, which is 1.88 meters per second at an angle of 56 degrees. So in order to add these, first I'm going to break each one down into its components. So let's figure out what my x and y components are for each vector. We'll put A and B. For vector A, to get the x component, I'm going to take 3.26 times the cosine of 20, and you should be able to do that on your calculator and get an answer of 3.06 meters per second. And as far as the vertical component, or the y component, you should get 1.11 meters per second. If we look at B, we have 1.88 times the cosine of 56 to get our x component, which is going to be 1.05 meters per second. And the vertical y component is going to be end up being 1.88 sine of 56, which is 1.56 meters per second. I broke each one down into its x and y components like we did in the previous example. Now I can add those up, and I get 4.11 meters per second in the x direction. I get 2.67 meters per second in the y direction. So my total x is going to look something like this, 4.11. My total y is going to look something like this, 2.67. Or we'll draw it over here, 2.67. So then my resultant will be facing that way at a certain angle. So again, I'll use my Pythagorean theorem like we did earlier to find that the length is 4.90. Again, a squared plus b squared equals c squared, so this is 4.90 meters per second. And again, using my tangent, which is equal to 2.67 over 4.11, the opposite over the adjacent, we get tangent theta equals 0.64. Take the inverse tangent of that, and we get 33 degrees. So that's essentially resolving vectors into their components and adding them. We'll do a little bit more with these in different directions later on, but hopefully you've understood the gist of what a vector is and how to add them together.